Hello, I am Jacob Field. I am in M144 Calculus with Professor Haruta, and I have class on Tuesdays and Thursdays from 12:45 to 2:25. For problem 1, we will be finding dy over dx for the following functions. This means finding the derivative. For problem 1, part A, we will be finding the derivative of 8x to the negative 7th power plus sine to the negative 1st power x cubed plus natural log of x to the 2/3 power. We will start off y prime equals d over dx 8x to the negative 7th plus arc sine of x cubed plus natural log of x to 2/3. For now, we are just doing algebra. To help simplify this, we're getting rid of that sine to the negative 1st x and just switching it to arc sine. Step 2. Plus 2/3 natural log of x. Alright, from here we are going to use our differentiation rules. We're going to do y prime equals d over dx x negative 7 plus d over dx of arc sine x cubed plus d over dx of 2/3 natural log of x. Alright, so this we're just splitting it up. Instead of having all as one, we're just going to break it up. From here, we are just going to calculate our derivative. So y prime equals 8x times negative 7x to negative 8 plus 3 arc sine of x squared times 1 over square root 1 minus x squared plus 2/3 times 1 over x. So as you can see, we took the derivative of this one here plus this one plus this one. That's how you do problem 1, part A. For problem 1, part B, we will be finding the derivative of 1 over the square root of 6x squared plus 4a, where a is a constant. For step 1, we will just be getting rid of the square root, and we will be putting y prime equals 6x squared plus 4a to the negative 1/2. From here, we are going to apply the chain rule. So it's going to be y prime equals 1 over 6x squared plus 4a to the 3 halves d over dx 6x squared plus 4a. Then, oh wait, forgot the negative. Okay. From here, do y prime equals negative 1 over 2. Oh, I forgot there's supposed to be 2 out front here. 2, 6x squared plus 4a to the 3 halves times 12x. For this part, we took the derivative of 6x squared. 2 times 6 is 12x. And 4a, since a would be a constant, that would mean it goes to 0, the derivative. Therefore, that cancels out. For problem 1, part C, we will be finding the derivative of y equals cotangent x over e to the 3x power. For this, we are going to use the quotient rule. So we will start with y prime equals d over dx cotangent x times e to the 3x minus cotangent x d over dx e to the 3x over e to the 3x squared. From here, we'll do y prime equals negative cosecant x squared times e to the 3x minus cotangent x times e to the 3x times 3 all over e to the 3x squared. We use the quotient rule for this problem to find the derivative. For problem 2, an object at the end of a vertical spring is stretched 5 centimeters beyond its rest position, also known as its equilibrium point, and released at time t equals 0 and observed for 2 seconds as it bounces up and down. Its position at time t is given by s of t equals 5 cosine 2 pi of t. For problem 2, part A is asking to find the velocity as a function of t. For this, we will need to find the derivative of the function that was given, which is s of t equals 5 cosine 2 pi of t. To find the derivative of this, we will do s prime of t s prime of t equals 5d over dt cosine 2 pi t. This is just showing that we are taking this and putting it out front. From here, we will do the derivative. 5 negative sine of 2 pi t d over dt 2 pi t. From here, we'll do 5 negative sine of 2 pi t times 2 pi. We took the derivative of this, and here we took the derivative of this. For problem 2, part B, it's asking us to find the acceleration as a function of t. In part A, we found the velocity as a function of t by getting the first derivative. To find the acceleration as a function of t, we'll need to get the second derivative, or we will take the derivative of the first derivative. This is what we got for our first derivative. Let's start off by simplifying it to s prime of t equals negative 10 pi sine of 2 pi t. From here, we're going to pull the constant out front. So it's going to be s prime of t equals negative 10 pi d over dt sine 2 pi t. From here, we'll use the chain rule, so that would be cosine 2 pi t d over dt 2 pi t. From here, we will put the constant back. Cosine 2 pi t. Then we'll do the derivative of this. The derivative of 2 pi t is just going to be 2 pi. And then from here we can just simplify this, all of this. We can simplify this to negative 20 pi squared cosine of 2 pi t. That's how we find the acceleration as a function of t. For problem 2, part C, it's asking to state how fast the object is moving at 1.5 seconds. To find this, we are going to use the velocity that we found, s prime of t equals negative 10 pi times sine 2 pi t. So from here, we will plug in 1.5 seconds into our t times sine of 2 pi 1.5 s 1.5 equals negative 10 pi times 0, which we know is equal to 0. So for the how fast the object is moving at 1.5 seconds, it has a velocity of 0. For question 2, part D, it's asking to find the equation for the tangent line to the function s of t at t equals 1.5. To start this, we are going to plug 1.5 into our original function that was given. So that's going to be s of t equals 5 cosine 2 pi to 1.5. Here, s t equals 5 cosine 3 pi, and this equals -5. From here, we are going to use our point slope form to find the equation for the tangent line to the function. So, we know this y plus 5 equals m x minus 1.5. We know this because we took the y that we found, y minus that would make plus 5, and then this was what we were given, our x, and that's how we find the point slope form for the equation for the tangent line to the function s of t at t equals 1.5 seconds. Thank you for listening to my presentation on problem for videos 2A for Calculus 1 of Professor Haruda's class that I have on Tuesdays and Thursdays from 12:45 to 2:25.